We do research, get new knowledge, but we part of passing that on is kind of reflecting both the knowledge, but also some of the pioneering people who helped create it. And certainly John Blume was one of those people. So just a few words about John Blume. Those of you that are students in our program know the Blume or Earthquake Engineering Center. There's some Blume fellowships around, but just to talk about the person John Blume for a few minutes. And so John Blume grew up in California. He was actually grew up just in the aftermath of the 1906 earthquake in San Francisco. His family lived there. And there was a number of kind of earthquakes through the early part, Long Beach earthquake 1933, and John was really fascinated by these. He did 3 degrees here at Stanford as undergraduate, engineer degree and PhD. And as you can see from the dates there, it used to take students a lot longer to get a PhD than it takes nowadays. So those of you that think you're working hard now. But no, John was a great believer in kind of lifelong learning, and he did some pioneering work and his engineering thesis I'll talk about in a minute. You can see that model there of the Alexander building that was part of it. He actually left and created what became a world-class engineering firm with some pioneers in their own right. But kind of between when he graduated in 1934 and by the time he had established this firm, and a lot of new technologies were coming on board, things like computers were invented, but also other areas here like probabilistic seismic hazard analysis that he was very curious about. So he came back to get a PhD in 1967. From the faculty at the time, there was a lot of trepidation at having John Blume in your classroom, which I could kind of appreciate. But I showed the Alexander building there, which is in the lobby of the Blume Center. You know, thinking about before digital computers and how we studied structural dynamics, a lot of it was through physical testing on shake tables. So this shows a picture of that building in action on the shake table there at the time. The shake table is interesting. It was built shortly after the 1906 earthquake, which really prompted a lot of the earthquake engineering research here at Stanford, across the bay at the other school, down south at Caltech. And interestingly, when I look back at that shake table, the first applications for that were actually not for structures, but for some of the reclaimed earth that kind of had large deformations around the bay fringes. So some of the earliest studies were looking at what we now call ground deformations and liquefaction. But John Blume, along with a number of other students at the time, worked with a faculty member from mechanical engineering, Lydic Jacobson, who's really a specialist in structural dynamics, and introduced, I would say, like rigorous structural dynamics into earthquake engineering, and also thinking going beyond elastic to inelastic behavior. And if you talk to Professor Miranda, he still goes back to many of the Jacobson and Blume papers of that era. As I mentioned, John Blume formed John Blume Associates, which later became part of the URS Corporation. Nowadays, it's part of an even bigger corporation, AECOM. But shown there is just a few of the very interesting structures that Blume Associates were either involved in did the design of, or were involved in special studies, particularly aspects related to either kind of state-of-the-art earthquake engineering and dynamics, or things that were kind of beyond the ordinary practice. I think in addition to these interesting projects, Blume Associates had a number of alumni, that is, people who worked there as young engineers who went on to fabulous careers of their own. People like Eric Elsesser, if you know the firm Farrell Elsesser. Eric Elsesser's first job was with John Blume. Someone I worked with years ago in New York, Les Robertson, who designed the World Trade Center. His first job was with John Blume. Sig Friedman, who founded the company, or the office of Wisjani Elsner. So there's this alumni of amazing people that kind of came through Blume's office, in addition to the ones that stayed. Marty Zarnecki, Joe Nicoletti continued to work with John. Some years after getting his PhD, John gave back to Stanford in a big way by kind of founding the Blume Earthquake Engineering Center. A couple of fun pictures from the past shown on the right there are the 2 founding directors of the center, Haresh Shah and Jim Gear, pictured there with John Blume at the shake table. Picture in the lower left, one I especially appreciate, Professor Karamidjian just a couple years ago. And you can't quite read all of the things in the picture, but if you could look above that little box that's in front of John, it says the computer. So that but again, as I mentioned, that was a time of Professor Karamidjian was at the beginnings of what we now probabilistic seismic hazard analysis. So John Blume was very interested in kind of bringing some of those ideas into practice for some of those special structures. And through the, John Blume passed away a few years ago, but through the Blume Foundation continues to give back to Stanford, supporting the center and a number of student fellowships. So again, kind of we just take this opportunity to reflect a little bit of that history. So with that, I'd like to introduce up Sarah Billington, who will introduce today's speaker.
Thank you, Greg. Yes, I have the distinct honor of introducing you to David Goodyear, who's our speaker this year. I've known David since, I think, around 1993 or 94, when I was in graduate school at the University of Texas at Austin, and I'll explain that in a second. So David is the chief bridge engineer for the firm T.Y. Lin International. He has his bachelor's and master's from Cornell University, and he started his career working for Stone and Webster in Boston, working on nuclear reactor containments. And for those of you who might know some of these names, I found out today that he was working with Jose Rosette and Eduardo Cauzel and Christian Meyer, a lot of big names in engineering. And then after a few years, he switched over to bridge engineering and worked with Arvid Grant out in Washington. And he worked on some of the first cable-stayed bridges in the United States, like the Pasco-Kennewick and the East Huntington. He formed his own practice in 1987, which then became part of T.Y. Lin in 1996. A lot of the structures he worked on are listed in his bio, and I'm sure we'll hear about them today. He's been active in the professional industries or professional associations as well, president of Structural Engineers Association of Washington, and chairman of the PTI Committee on Cable-Stayed Bridges. Very active in the American Segmental Bridge Institute, which is where I met him when I was working on segmental bridges in grad school, and also with PTI, Post-Tensioning Institute, and AASHTO, the Bridge Code. And he is the recipient of the Beavers Organization's Outstanding Engineering Award for his work in engineering and construction of arch and cable-stayed bridges. And I just learned that this is particularly significant because that's an award given by contractors. And they gave it to him, not a contractor. And he's also been elected, or is a member of the National Academy of Engineering and was elected into that in 2013 in the same class as Professor Dearline. So with that, I would like to welcome David.
Thank you, Sarah. So the topic of my presentation is to think like an engineer, and that not meant to be presumptuous, but in terms of thinking like an engineer, as a design engineer, at least when you encounter a challenge, a project, your first visualization is to look at the solution rather than the process to get to the solution. And I think that's one of the things that in engineering, when we approach issues that is somewhat different than perhaps the more rigorous approach to analytical work or academic work is when design engineers sit around the table, they debate the answers somewhat without regard to how you get to the answer, which is later on in the process. I want to just, in terms of the outline of my talk, first explaining myself and my background a little bit more than what Sarah's, Professor Billington has explained, just so you understand my perspective, so you have more of a basis for disagreeing with me if you like. And then talk briefly about the influence of engineering heritage on what we do, particularly in bridge engineering and civil and structural engineering. Talk about the character of designs in terms of how they fit the theme of thinking like an engineer and making things simple, and then finish with a couple of notes on codes and cautions in using codes and contemporary analysis. So for myself, as Professor Billington mentioned, I went to Cornell University. I had the pleasure of being educated by a fantastic faculty. But when I left Cornell, I felt that I knew a lot that they taught me, but I had no idea whether it was any good and how I would apply it in practice. I really didn't know what was going to be necessary in order to be a practicing engineer. I went from there to Stone & Webster, which was just like graduate school for me with the people that I worked with, and was basically worked as an apprentice, if you will, learning what other people knew and were anxious to teach me. It was a fantastic opportunity working for that company for the first 4 years. And then evolving from that into engineering practice, where particularly once I became a bridge engineer, of learning more as time went on with every project and learning very much more what I knew and having confidence in my abilities of what I could do, but also getting to understand what I didn't know. And the more that you become accomplished at a particular field of engineering, I think it's fair to say the more you appreciate that what you don't know you shouldn't be doing. And that there are plenty of people, experts out in the engineering field, that when you get into certain specialized activities that you're not well versed in, that you need to employ them and not try and make up for the lack of experience that you have. As I've gone through continuing education, which we have to do for licensing, after 40 years of continuing education, you kind of run out of classes. Actually, after about 15 years, you run out of new classes. And many of the continuing education classes I've taken in things like tunneling and earthworks and all sorts of things that ASCE offers have taught me that I have no business doing tunneling work and some of these other things that don't relate to my experience as a bridge engineer. I was very lucky to have a mentor when I went into bridge engineering. Actually, I'm a bridge engineer, which is a credit, I guess, to my wife, because I was getting ready to go back to graduate school, and she was not interested in me going to graduate school, so she actually saw the ad in the newspaper that Harvard Grant had. She handed me the ad and said, "Go talk to this guy and see if he can convince you that you don't need to go to graduate school." So, and he did. I went in, I expected to spend a half hour, and 4 hours later I had a new job and never looked back. He was educated as an architect, a Latvian architect, and he came here after World War II and set up a practice as an engineer. He first worked for the State Department of Transportation, and that was not exciting enough for him, so he walked out the door one day and set up a practice by himself. I remember him telling me that he was a bit naive. He set out a shingle and he thought people would come and knock on the door and give him work, and it wasn't long before he figured out that it didn't work that way and he had to go out and find the work. He was a brilliant individual, and he probably defied my early example of not doing what you are not expert doing, because he did mechanical design for the timber industry out there. He taught himself to be a surveyor, and which is rather arcane practice actually of understanding local survey rules and things, and he had a survey practice. But he was a great person to work for, partly because of his approach, his attitude about being a bridge engineer. First of all, he thought being a bridge engineer was the best profession that on the face of the earth, and that rubs off when you work for somebody like that, who has such dedication to what he's doing that is a great environment for you. But he gave more ethereal lectures than engineering lectures, frankly. He was an amateur philosopher. And he said that the work of a bridge designer should meet 3 criteria. It should be structurally correct, which goes without saying, that makes it stand up. Should do the most work with the least material. He was a stickler for efficiency. He didn't want an extra pound of anything in that wasn't necessary or justified. And it should not cause injury, physical or emotional. The emotional side was his perspective on architecture. He was not one for embellishment, but he was one for what we now call context sensitivity. He wanted things to be efficient, and he felt that if your design was efficient, it would not cause emotional harm. But if any of you knew him, which most of you I'm sure didn't, but he was quite a personality. He was an irascible old fellow, and he was frankly tough on some clients and great with others that appreciated his personality. But the little drain at the bottom there was a little sign over his desk on persistence. This is a quote attributed to Calvin Coolidge. It's attributed to a lot of people, but basically saying that persistence is omnipotent. And if you're into design and you have a vision for a design, and in his case, whether the client liked it or not, if you had the right answer, you had to be persistent and see it through. And that was certainly an explanation of Arvid's personality. But getting to the influence of heritage, we do think that we know a lot these days, and that we have that we're pretty special and have great capabilities. But one way to remain humble is to go back, and I do enjoy history, I have to admit, and look at the Roman engineering. And there are many examples of that. But when you stand in the Pantheon and look up at that ceiling and see how exquisite it is, and realize that it was done 2,000 years ago, and that you'd be hard-pressed to have that built today and not have patchwork done on the inside. When you look at the Colosseum, and depending on which tour guide you believe, it was built took from 6 to 8 years, and realize that it took almost 7 years to build the Safeco Field in Seattle. You look at the Pont de Gard and Alcantara Bridge. The Alcantara Bridge in Spain carried tanks in World War II. They didn't have tanks 2,000 years ago. The Pont de Gard you can drive across today. The ability historically of people to do some of these fantastic works without the tools that we have today was extremely impressive, and a lot of what they do has lessons for today, one of which I'll talk more about in a second. Brunelleschi is, this Florentine Dome is kind of a favorite, mostly because I still look at it as a brain teaser. I was mentioning to some folks at lunch that there are people there even today, or certainly in the last few years, that are trying to build miniature models of the Florentine Dome to figure out how Brunelleschi got a pile of bricks to form that dome, his 35 or 40,000 tons of brick. And simply how being able to build that was a marvel in its day. Brunelleschi was a generation, or at least a half a generation, probably a generation ahead of Da Vinci, and I think would be probably in engineering circles might be just as well known as Da Vinci if Brunelleschi wrote down as much of his thoughts as Da Vinci did. Da Vinci wrote down everything, and Brunelleschi wrote down nothing, because Brunelleschi was more concerned about somebody swiping his ideas than he was about leaving his ideas for posterity. But if you like a little analytical project for those of you that like nonlinear analysis and sit down and figure out how you use the efficiency of structural form to make this arch stand up as you're building it up from the bottom with these rings, I think it's a fascinating subject that really teach you how spectacular these old engineers and craftsmen really were. And then a little bit more modern, but Gustav Eiffel, and when you look at the Eiffel Tower and you look at that lattice work, realizing the Eiffel Tower was originally built to be torn down. It was built for an exhibition, and they decided they didn't want to tear it down, which is now the icon of France, actually. But the metalwork and the detailing of which is really from a behavioral standpoint, the tension stiffening that is part of the structure here, similar to his Garabit viaduct. This viaduct he built in about the late 1800s has some lessons even for today. Some corollaries I'll also talk about here in a moment. Pulling the historical concept into contemporary context. On the left view there is one of the crowns on the Pont de Garde, a picture that I took a close-up. And you cannot get a knife in between the joints on those cut stones. On the right is a view of one of the columns on Hoover, Hoover Dam bypass bridge, which I'll talk more about in a little bit. And the assembly of, it was precast segmental construction for that column. As Hoover was being developed, we had a delay in funding that shut the job down for about 2 years after we finished design. And in that time, we put the plans out publicly on the street for contractors to take a look at to get feedback. Obviously wanting to get some input on how we could improve things and make the project more cost effective. We had an outreach meeting once the project started back up, and we had about 100 contractors in the room, contractor staff in the room. And one of the things when I gave the initial presentation, a few of them had some epitaphs for me saying that building a 90-meter tall precast concrete column was crazy and that you could never get it straight. Nobody had done anything even half the height, and it was not possible. And I knew this was coming. Had some spies out in the network. And so I pulled up this picture, and I explained to them that what I learned at the visitor center there, Pont de Garde, was the way the Roman masons did it was each one of those blocks has initials carved in the back. And the initials are of the stonemason. And if the stone fit when they got out to the Pont de Garde, the stonemason got paid. And if the stone did not fit, he did not get paid. So as a result, most of the stones fit. And I encourage the contractors that if you took the same approach to your precast segments, I'm quite confident that you can get a 90-meter tall precast segmental column to work with all the cranes and the theodolites and all that you have today. And those poor masons had a sand saw and chisels. I'm confident that you can get it done. And actually, the Japanese contractor did an exquisite job of casting, and the erector of these columns had never erected a piece of concrete before in his existence, an outfit called Olsen Beal, and the columns are straight as an arrow. You can eye right up the bead of that column, and it's perfectly straight. So in looking at design process, again, going back to the theme of think like an engineer, and the reference to design process here is tailored towards the type of projects that we do, which are somewhat competitive, usually either a design build or what we call a P3, public-private partnership, which is private financing and a design build underneath it. There is a process to go through that where the client generally defines the basic requirements, but being competitive, the first thing you look for is what options and opportunities you have to be competitive and beat your competition. And all of this is factored into this gray matter that's your experience and education, part of which many of you are getting now at the university, and you will get an awful lot more in practice. But that filter, out of that filter comes your concept, your conceptual design, and you don't start with the answer, you start with ideas and an array of answers, and you test those ideas through analysis and testing to get down to a refinement of what your basic concept, basic configuration that you think is most advantageous and most competitive. And there are a lot of factors that go into this, service life, durability. The factors for competition are established by the project requirements by the owner. And if it's competitive, you pretty much strictly follow those competitive requirements. And if you get too far astray from that, you're likely to have a nice picture but not a job. But at the end of that concept development, what you have is really the definition of your project. At the concept stage, you pretty much defined the economics of your project, of your design, the character of the challenge of difficulty of construction. All of this is really established at the conceptual stage. And then you get into your detailed design. And in your detailed design, oftentimes you'll find out that the assumptions you made in your concept were perhaps a bit oversimplified. And that's where you draw on your analytical and technical capabilities to grind through those surprises, but you're still really developing that product that is established at the conceptual stage. So the conceptual design phase is really where you make or break your project. Going into some examples of, I hope to make the points of this process. I'm going to talk about arches and cablestay bridges because of the long span bridges. That's mostly what I've done. So, and there are other people that would get up and talk about suspension bridges, perhaps, and other things. But in terms of arch, of course, an arch is. I explained this. I told Professor Billington I've taught bridge design to 4-year-olds in my daughter's preschool class. So excuse some of the analogies, but arches are like eggshells, and you give a kid an eggshell and tell him to squeeze as hard as he can, and he can't break it. And as soon as he tries to bend it, it breaks very easily. And that's the concept with which you approach an arch design in terms of efficiency. It was the first long span bridge form. Historically, the bridge on the top is in China is 1,500 years old. It's one of the first open spandrel arches, and it's still in service. There are a variety of layouts. The classic parabola is at the top, and the cathedral arch, which is basically an interior pier in the form of an arch, has a compound circular shape, and the funicular curve, or the balance of arches are curve fit. I'll explain the funicular curve in a minute, but all of these are geared towards, the shapes are all geared towards minimizing bending moment and maintaining the efficiency of form. In terms of that efficiency, one of the elegant solutions for arches is called the network arch. This Brandinger Bridge on the right is a contemporary bridge designed a few years ago. The one on the upper left was designed by an individual by the name of Per Tvedt. He's a professor in Norway who happened to have, I believe it was his cousin, I don't remember his cousin or his brother-in-law, he told me, but that was the highway director in they're not called highway directors in Norway, but who let him build this bridge because nobody else would. And he developed this network concept, and the network concept is you have to have each diagonal hanger crossing 2 hangers, and when you do that, you find that the buckling stability of the arch is enormously enhanced with the same kind of implicitly tension stiffening that you saw in the Eiffel Tower, and basically a system strengthening that you get by if you're disturbing the arch in one area through displacement compatibility of these hangers, you're actually going to pull the arch, add the stability of the arch. Because obviously one of the ambitions with a steel arch is to avoid the penalty that you pay in steel for stability. So if you can get the arch rib to be limited by the strength of the steel, then you've got an extremely efficient structural system, which is what he developed now. Of course, he developed this at a time where, again, like the discussion of John Blume, he did this in the laboratory without computers. He told me he did a lot of finite difference calculations. I don't know how far he could go with that, but most of it was done in the laboratory. And this is today, again, getting back to the load curve fitting, the Brandinger Bridge is more circular than parabolic, but it's all shaped to minimize the bending moments in that arch rib, which is how you get that such an efficient structural form. Now, obviously, maybe not obviously, one of the challenges with this type of bridge is how do you build it? Because while the network arch is extremely efficient as it's put together, putting it together and getting it out there is another matter. This Brandinger Bridge was floated out as a unit. Père Bridge was built on false work. But in terms of ultimate design efficiency, that system approach, the concept, has been extremely efficient. And there are bigger arches being done. These super light bridges are all two-lane bridges, which obviously you have less demand on a two-lane bridge. But even today, there's quite a number of network arch bridges being built in the U.S. that are take advantage of this type of system design. Going back almost 100 years now to the days of Robert Maillard, had a very similar concept system design approach to concrete bridges, where if you look at how slender the arch rib is, you wonder how you can deal with buckling, and what Robert Maillard, who ran pretty simplified calculations, most of the hand calculations, realized that the arch rib has to be there's displacement compatibility with the deck, and the deck is stiff enough. The arch doesn't need flexural stiffness, so basically he could design that arch rib as a pure compression member and built the arches in a reticulated fashion. And a modern rendition of that is from Christian Mann on the right, where you can see, just because of the view, the linear elements between the spandrels, the reticulated configuration, which if you look at, actually the curve on the right is taken from the numbers in the older Professor Billington's book on Robert Maillard. But the principle applies universally. The optimization on the right is simply for a rectangular arch rib and a relatively narrow deck because of the ratio between the influence of the deck and the arch. But on the left, you see that the arch moment ratio depends, no matter if you take this into account and analyze or evaluate your arch as a system, it's a universal principle. Whatever your stiffness ratio is where you drive the moments. So in both of these cases, looking at this funicular curve for a deck arch, it's pretty simple to develop it. You look at the equation here is based on assuming all the loads are horizontal, but you can modify it for the inclination of the arch. And you're basically looking at following the moment diagram at the point of your spandrels so that you have zero moment from whatever permanent loads you assign, and get a theoretical profile that is free of moment. Having an arch made out of concrete, that doesn't last very long, which I'll show you about in a minute. But this theoretical curve, for instance, for the Hoover Bridge, which was laid out this way, the arch rib was, for other reasons, was quite a bit heavier. So counting the arch rib itself in with the deck and looking at all the weights, the funicular curve varied from the parabolic curve by about 2 feet in certain locations. But it basically was designed, set up to have this same target of zero moment. In looking at the form and the concept for Hoover, just by way of background to how sometimes you stumble into your answers, the Hoover Bridge was being put together. We were putting together concepts. This conceptual stage was going on at the beginning of the project when the geophysicists, the geologists were out scouring the landscape around Hoover Dam. If you've ever been there, it's kind of like a moonscape. There are just rocks and scarps all over the place. And the geologists mapped all the scarps for miles around, and they decided that they were going to connect them all with a line. and define that as their fault source. And they came back and they said that we could have a 0.7 G earthquake event at Hoover Dam. And I said, well, first of all, Hoover Dam won't be there if you have that 0.7 G event, or at least none of the facilities will. But while I was skeptical, I was also intimidated. So the clip on the lower left, which most of you probably don't recognize, but that's actually the tower that I developed for the San Francisco-Oakland Bay Bridge for the Cablestay alternative, which didn't see the light of day, except for the design of these shear links. The tower was, for the Cablestay, was developed to have elastic vertical elements and inelastic horizontal elements. So all of the ductility demand would be taken up in these fuses. So I thought, well, I could try the same thing for Hoover, so that if we had this huge seismic event, I'd at least have a mechanism that I could count on as a ductile mechanism, because putting a plastic hinge at the base of an arch isn't the best idea in the world. It turns out that after asking the geophysicist to go back and give me a return interval, recurrence interval on the earthquake, it was something like 40,000 years or whatever, and I said, give me one for 1,000. So the earthquake level came down, and eventually the wind design governed marginally over the earthquake. But that's the main reason why we have a split arch rib there. The split arch rib also helped from a constructability standpoint, because a full arch rib would have been much more challenging from a construction standpoint with form travelers and things. And we had hoped to have a precast alternative. We didn't have one in the end. The chamfers, when the architects that were writing the pieces at the end of the job for the visitor center started talking about the sculpting and shaping the arch rib for architectural reasons, I had to tell them that I'm sorry to disappoint you, but it has nothing to do with architecture. It was I don't know if any of you knew John Raggett at Westman Laboratories. We stuck the and the chamfers cut the drag down by 30%, so that's why it has chamfers on it. The tall columns only have a 1-foot chamfer on them, which analytically would say would be too small to quell vortex shedding, but in the wind tunnel it did. When we had rectangular columns, they were like tuning forks in the wind tunnel. So all of these aspects came from engineering origins of looking at behavioral aspects, and these were all developed at a fairly conceptual stage before we got into final design. There's the last three, the framing system and creep deflection, the stiffness, we had to concern ourselves with pedestrian comfort, but that was all part of the design here that I'll explain here going forward. The nonlinearity is something, I'll mention it towards the end when it comes to dealing with nonlinearity in structural design or bridge design and particularly construction, but the upper right is quite exaggerated, hopefully, view of the creep in the arch, which the reason is to show the distortion that you get in the columns. And 100 years ago, when people designed open spandrel arches, if you go back and inspect them now, they all have cracks in the columns. It doesn't seem to bother much of anybody, but today, since we can analyze it and predict the cracks, it bothers everybody. So we put in these expansion bearings to allow the columns to breathe so that we didn't get cracking in the columns. And Professor Billington actually was giving a paper about the time we were close to being done with this design, talking about a concrete that had high creep coefficient and high creep properties, which would be ideal for this situation, because if you had a high creep coefficient in those columns, because the settlement of the arch is time dependent, it takes quite a while, you would just relieve the moment due to creep. But I actually approached Federal Highways about trying that as an experiment, and I was turned away. They said this was too big for a demonstration project. But the other aspect of the nonlinear response is the tall columns. This column is about 90 meters tall and is about 2.5 meters at the base. It's a very slender column. One concern I had was that, as you know, nonlinear structures don't respond in the sense of superposition. So when it would breathe during thermal expansion, I was concerned that the big columns wouldn't come back, that we just get a bow in them. So these springs at the end were designed to overcome the stiffness of the columns and push them back under temperature changes, so that we controlled everything by displacement instead of worrying about forces. And like I say, I'll talk more about that when I get to Cablestay bridges again, because it's more pronounced in some Cablestay bridges. Then the deck, there's no bracing in the columns. We didn't want bracing in the columns, so the deck serves as a diaphragm from abutment to abutment to brace the entire bridge, longitudinally and transversely. So we needed to create a diaphragm. So this approach to this was a composite, steel composite deck, and we need to have it continuous over almost 2,000 feet. Sitting on, the traditional way of doing it would be build a portal frame and sit it on bearings, but that wouldn't give us the stiffness we wanted, especially the lateral bracing. So we came up with this detail of post-tensioned shear plate. We didn't use a steel cap because in the bridge community you have something called fracture critical design, that if you have an element that if it fractures would cause collapse of the bridge, there are a lot of special rules and special expenses that go with it, not to mention the inspection that has to take place every 2 years. So we opted for a concrete, post-tension concrete solution. So then we had to connect the boxes to the cap, and this connection on the lower right is what we came up with, which is a serrated plate, which I'd actually used years before for a very heavy construction load, because shear friction with a steel plate to concrete, while they're good, reliable numbers for it, if you clean the steel plate, if you're out in the field and somebody gets oil on the plate or something, there's some concern about how reliable it is. So we had this serrated plate, which worked exceedingly well. And when I used this in the past, you actually could take the PT off of there. There's a draft on the cap so that even if the PT disappeared, the connection would still hold. In terms of tuning the arch, most arches, even some steel, a lot of steel arches, classically when you're ready to close the crown of the arch, you'd put jacks in and jack the crown apart. And that's to try and target, again, something closer to a zero moment at the springing, because arches don't like moment, and the efficiency, the material you need to put in can be excessive. Actually, it's not entirely clear that even for cast in place arches you really need that always. But here, that was something that was that the reviewers commented on at the beginning, the Federal Highway people. But since we erected this with stay cables, we could control the moments in the arch rib by tuning cables, and it was pretty easy with these backstay cables, the ones from the tower going back to land, to just pick the whole arch up and pre-camber the moment into the springings. So we could control that moment, and recognizing that creep in the concrete will always creep towards the final statical system. But we had, this was 10,000 PSI concrete, we had very low creep specific creep, very low creep coefficient. So whether we were fooling ourselves or not, we thought we could pre-camber this and predict that we could target a zero moment. We used a higher creep coefficient than we got out of the testing, so we probably have a positive moment instead of a negative one, but we were designed for that envelope. This is an earlier arch that we designed in Oregon. that also used cable-stayed methods for construction. And one of their 2 points I want to make about this, first of all, the integral crown, which is a feature of this arch, would have helped the stability of Hoover perhaps somewhat, although the springs were sufficient at the end. But what we learned on this smaller bridge was that it cost as much to build that integral crown as it cost to build all the rest of the arch. So when we got to Hoover, we purposely, if Hoover would have been a longer span, which was one of the options, we would have needed an integral crown for bracing the arch rib, but for the span we had, we didn't need it. So we had reasons to prefer an open spandrel for Hoover. But this arch was built in what I call layers and successive castings. It was a trough section with 2 edge girders and a connecting slab. The arch ribs were built first, the 2 edge girders on a form traveler with cable stays, and then they just flew in the forms and built the slab later. So if you're looking at it analytically, you don't have the whole section. Again, concrete is time dependent, very age dependent. You don't have the whole section all at once, and you have to figure out how to evaluate what are the stresses and demands in that type of construction, which I'll highlight that at the very end as to different ways of looking at that. And moving also to cable stay bridges, which again I think fit the tone of the theme of thinking like an engineer and making things simple. The cable stay bridge, while it can look complicated, it's actually quite simple, probably simpler than an arch in a lot of ways. If you look at it, the analytics of it are complicated because of the high indeterminacy, but the concepts are pretty simple. There's 2 approaches to cable stay bridge design in terms of the deck. There are flexible decks, which concrete edge girders like Dame Point and concrete cross beams. Sydney Lanier is that way. There's composite, which is the most popular in the U.S., which is a steel frame system with usually precast decks on the top. And then there's a box girder like Sunshine Skyway in Florida that behave quite differently. The lower one is Cap Shui Mun in Hong Kong, which has a train in the middle. So if you have a train in the middle, you're going to have a double deck. You're going to have a stiff box. But these approaches, they have their advocates, and they usually don't see eye to eye. Jean Mueller on the right and Arvid Grant on the left were friendly towards each other until they started talking about the merits of a flexible versus a stiff cable stay bridge, and then they weren't that friendly anymore. If you think of a nonlinear structure and you look at East Huntington there hanging there, that's pretty good candidate for nonlinear behavior before you close the bridge. And the bridge on the right, of course, that stiff box is, in terms of geometric nonlinearity I'm talking about, is really is not at all nonlinear. But what you have in terms of the merits is the conceptual approach to the flexible bridge is that the cable is the most efficient, this cable intention is the most efficient element, and you want to maximize the use of that cable and what that cable can do. The concept with the stiff bridge, with the box bridge, is that you want to actually minimize the demand on the cables and use the properties, the torsional stiffness, for instance, of the box, and the flexural stiffness of that box spreads out, concentrated. If you look at the fatigue demand on the cables on the right versus the left, the fatigue demand on the right is less than half of what it is on the left. So, and that's why, in terms of development, I think Arvid was certainly influenced by Leonhardt, Professor Leonhardt, who was very focused on fatigue. He developed something called a high-M anchor. It was very high fatigue capability anchor, whereas Jean Mueller said, I can just use a post-tension tendon. I don't need to worry about that. So his first Breton bridge, which was a predecessor of Sunshine Skyway, just had pretty much regular post-tensioning technology for the stay cables. So both of them, both approaches have the merits. With a box girder, you only need one plane of cables because you have the torsional stability. Obviously, with an open section, you don't have that. You have to have two planes of cables. So philosophically, they both have their advantages, and it just depends on how you want to approach the design. In terms of the behavior of these, like I say, these bridges are actually pretty simple conceptually. You can look at these where they get within 20% of what you need to know with a beam inelastic foundation calculation that, say, you could do it on the back of an envelope, but now you do it in an Excel spreadsheet. But one of the interesting points, I think, in terms of the historical perspective is I'll say in Germany, my frame of reference in Germany is Leonhard Andra, is Professor Leonhard. Early on, they designed their cable-stay bridges for lane loads as fatigue, which of course is applicable for a railroad bridge. But if you look at simulated live load, is not necessarily very reasonable for a vehicular bridge. So they had this influence line. Cable 1 is the influence line, this Pasco-Kennewick bridge, for the backstay cable. And if you look at a uniform load pattern, of course, and apply that to fatigue, that's a very high fatigue demand, or your highest fatigue demand. And that's really what prompted Leonhard to develop his high-M anchor as opposed to using post-tensioning. But if you do a traffic simulation, you'll find that backstay cable actually sees less fatigue load than some of the interior cables from an actual highway traffic perspective, which is what Jean Mueller was happy to inform people of. Again, with nonlinearity, and this is the main point in terms of dealing with nonlinearity that I want to make. The classical approach to analysis that I'm sure you all use is you develop a stiffness model and you apply forces, and out of that you get stresses and moments and deflections. That's the classical way of looking at an engineering analysis problem. With a flexible steel bridge that you have to analyze all the way through construction to know where you're going to end up, that just doesn't work very well, because first of all, you might have in the jacks where you think you're putting a load into a cable, you might have a 3 to 5% tolerance on your jack readings, and you have a very flexible system. And actually in the limit, it's like a weight on a string. If you have a weight on a string, you can pull that string up and down as much as you want, and the tension in that string doesn't change at all. And that's what happens when you try and erect a flexible steel bridge with forces, is you can't control the deck. So you really want to go into a nonlinear system and turn things around a little bit and control it by displacement. Whether you're building dealing with a nonlinear column that is guyed off or tied off as it was in Hoover, or you're dealing with building a flexible bridge, you want to control it by deflections, because as I'm sure you know, that if you know the unstressed shape of all the elements in your structure, and you know the stress shape of of your final structure, for a linear material, everything, all the stresses in the structure. You don't need to analyze anything else. You can just look at strains and curvatures. So when you put the bridge together, the caveat is, of course, you have bolted joints that have some tolerance in them, but as you put the bridge together, you can easily monitor that to know what your variances are. You do have creep and shrinkage of the concrete deck, which generally for precast decks isn't a huge factor. So you really can establish, and sometimes it's difficult with owners to let them know when they get readings from the contractor that the jacks are off, and they get excited about having their bridge building correctly. If you go out and show them the geometry, you have to convince them that if you know the geometry, you know the answer, and the jack reading is probably wrong. Conversely, for a stiff box, you can't move it from its unstressed shape. As it goes together, you need to erect that by force, because if you tried to use the same methods you use for a flexible steel, you'd break the cables. So if you have to make geometry corrections there, it's quite different. With a flexible steel bridge, you can pull it around quite a bit. For a stiff concrete bridge, if you have to change it, if it's cast in place, you have to change the form trowel, or it's precast, you have to use shims. Talking about, moving on to another a project, the last project here is Port Mann. This is a bridge that we did a while ago up in Vancouver, BC. And again, trying to explain how we got to the solution that we arrived at was pretty simple. In fact, embarrassingly simple, actually. This is the layout of the bridge, and up to the top, I hope you can see there are two lines up there, which was the old bridge. This was a project with the criteria was they wanted 10 lanes crossing the river. And the concept that the owner put out, this is a P3 or bid as a concession project. The owner said, I want 10 lanes when we're done, and the concessionaire, you have to take care of this for the next, it was 35 years, counting construction. So you keep the old bridge as long as you maintain it and build a 5-lane new bridge. Well, the financing people looked at the same report we did on the old bridge and read all the assays of fatigue cracking and crack repairs. The old bridge was actually a very nice old steel arch. And they said, we don't want any part of that old bridge. We don't want to take care of it. So give us a design where we take out the old bridge and build 10-lane new structure. Well, we had right-of-way for 5 lanes, and we had to stay within the right. It would have taken us years to get additional right-of-way and millions of dollars, hundreds of millions of dollars. So we came up with a single tower solution, the purpose of which was to get that footing to fit within the right-of-way. And that's the sum total of the logic behind that concept of building 2 bridges and hanging it off of 1 tower. It was an interesting exercise to design the tower for 4 cable planes. The geometrics had to change. The tower had to be taller to get traffic underneath the splay of the cables. And there were a couple other interesting engineering items that we had to take care of. But it was basically pretty simple just 2 decks supported off the same tower with a strut in between to take the splay forces out of the cable, and everything else was very normal. That's why it was bid very competitively, because this was all something that a contractor had built before other than the tower. And off the ends of the bridge, the approaches are precast segmental boxes, so we split it into 3 so that the 3rd box we could build after we tore out the old bridge, because at the tail ends of the bridge we overlapped with the old highway and ultimately had to maintain service throughout the construction period. But one of the details that had to be attended to that is somewhat different is the stay anchor for this bridge, for the outside stay anchors. There's 2 types of anchors. Again, this is just like the difference between a slender deck and a stiff deck. There's a semi-religious affiliation with some of these stay anchor types. And there's the top 2 anchors are called fin-type anchors, where basically the web plate of the edge girder is extended up, either welded onto or bent plate or continuous plate. And for our case, and in other cases, you can either bend the plate to get the draft on the display on the cable, which is done, that upper left is the bridge in South Carolina, in Charleston, South Carolina. Ravenel Bridge has that type of detail. Or put a cant on the entire outside girder so that the plate is straight, you don't have the bend. But in both cases, you have a concrete deck cast around that connection area, so you can't see it, you can't inspect it, and you certainly can't replace it. The lower anchor, it was an external, we call it a bucket anchor on the outside, is either a pipe or a steel box that we bolt on to the outside edge girder. If you had to, you could take it off and replace it. But the main issue here is that these lower anchors have to be stiff enough to mobilize the damper on the stay cable. Because if they're too flexible, the damper will just shake with the cable. So you have to generate motion within that damper in order for the damper to work on the stay cable. And certainly in the plane of where you have a vertical cable plane and the motion you're damping is within the cable plane, that fin anchor works just fine. But if the motion is out of plane, it's not very stiff. So the bucket anchor is somewhat, the stiffness is two-dimensional so that you have sufficient stiffness all the way around. One other point, well, a corollary to that really is that when you look at the cable plane, which is tilted in to meet the tower, the bridge cable is, the change in sag is always vertical. And so you have out-of-plane movements, and this actually can put, with a large splay like we had on Port Mann, this can actually put a lateral component on that plate, which, like I say, is buried in concrete that you can't see. And so if you had any issues, fatigue or otherwise, it'd be a bad day when you found out. So one of the things in closing here is the notion of an old man's advice to young students is to really think for yourself. One of the things you'll be dealing with if you get into design world is codes and standards. And the first point is that codes really don't help you design at all. Codes are used to validate the design that you come up with, but they don't help you get there really. Certainly the background in knowing and understanding codes and having experience is going to be part of that experience, the bubble that I mentioned, that knowledge and experience, but you're not going to find anything, at least for these types of bridges, in a code that says this is how you should design this bridge. They're focused more on conventional designs, although of late they're becoming far more voluminous. That picture on the left is a little bit more than half of the Euro code. We only buy the part that applies to bridge design. The picture on the right is the AASHTO code, which is also quite voluminous. This is one of the handicaps of modern technology, because now that you can carry the code on a thumb drive, I think people are less inclined to make the publication efficient. But they're basically methods-based specifications that seek to tell you how to do everything rather than what you should achieve at the end of what you're doing, which would be a performance basis. They're definitely essential, and you have to have a code to validate your design. I think performance-based specifications are much preferred. On PTI, we tried to push the PTI recommendations that way for many years. There is a move to try and get the AASHTO code and other codes to be more performance-based, but it's a long process. In terms of items of caution, just by way of example with codes, realize that when you're using the code, it was based on the best evidence of the code writers at the time, and that input was probably at least 5 years before you're using the code, because of the cycle on a code. 5 years is fast, actually. And you have to be cautious about blindly applying codes in all situations, especially when you're looking at unique aspects of design. And here are a few examples I'll run through quickly here. One is, the first is durability. Durability is underappreciated in the U.S., in the U.S. Bridge Code. People are paying more attention to it now. The European codes are more developed in this regard, and one of the standards that's found its way into the Eurocode and elsewhere is this FIB Bulletin 34. The premise of that, as it's applied worldwide, is that if you design to the balance of the model code, that you can apply these reliability-based forecast of your service life, the methodology of which is in Bulletin 34, and that you'll have a durable structure that you can forecast with some reliability the service life. That Eurocode, the general provisions allow for generally a crack width of anywhere from 0.2 to 0.3 millimeters. The crack that you see on the right is about 0.12 millimeters or 0.005 inches. So the crack that you're allowed in the Eurocode under the principles of this, at least under the practice of this, is about twice as big as the crack that you see there. And this crack got the attention of everybody. A crack twice this size, I think you can look at it for yourself and appreciate that chloride-laden water is going to get into that crack. And so the assumption that your chloride permeability is anywhere close to uncracked concrete is not very valid, yet that's the premise of the design approach. Now, there are other mitigating factors of if the reinforcing is normal to the crack versus along the crack. You get a much different answer, but you have to be a bit circumspect when you apply these criteria to make sure that for a column that's out in the atmosphere and you're worried more about as much about carbonation as you are about chlorides, it's fine, but you have to recognize that for some cases, like the deck on a Cablestay bridge, if you had cracking like this, it would not be a good idea because it's pretty difficult to replace that deck. Now, this odd picture that you see in the middle, I've had on my desk for about 30 years. And I'll admit that I'm not a fan of epoxy-coated steel, so I tell that before I tell you this story. This was a spall that came off of a post-tensioning detail on a bridge I was working on at the time in Oregon. And this spall came off at about half the load that was predicted to spall concrete. And as soon as I looked at this, I realized, that this was actually, this might have been the first job that I worked on that had epoxy-coated steel. There's absolutely no chemical adhesion between that concrete and the steel. You might as well wrap the reinforcing in cellophane. And what happens, aside from that aspect of durability, is that I've seen in other cases since then where you can actually get shrinkage away from the rebar and get an annulus where water can get in there. And in cold climates like Boston, you can get spalling that looks just like rusty steel spalling, except it's ice spalling. The other aspect of epoxy-coated steel that is not advertised is that there's a big bridge in Florida that was built with all epoxy-coated steel 25 years ago. And today they're looking at putting impressed current on that bridge to protect it from corrosion, which means they have electrical connectivity and all that epoxy-coated steel sufficient to put on cathodic protection. So from the standpoint of epoxy-coated steel, certainly epoxy-coated steel in the laboratory works great because it hasn't had iron workers climbing on it or vibrators banging it and all the other various and sundry things that affect the epoxy. But my view is that if you need, while epoxy-coated steel is very heavily endorsed in the AASHTO code, if you need to really rely on a durable bridge deck, that you just better pay for the stainless steel. Another aspect of caution with the codes, or example of an aspect, is there was a time here in California where when precast segmental construction was being introduced, it is most efficient at times to have external post-tensioning that's not bonded, except at deviators sometimes. And so there was a rule promulgated that if you had a precast segmental bridge, that you had to have half of the steel bonded and at least half the steel bonded, and you could have the other half unbonded. Well, you do a strain compatibility analysis, and pretty quickly you realize that before you mobilize the strength of that external steel, you're going to break the bonded steel. So these incompatible system, it was a very incompatible system that was stipulated at the time, which they soon after Frieder Seible at UCSD pointed out from his testing that this was not a good idea. That was dropped, but it was in the provisions for quite some time. And then being the Blume lecturer, I have to say something about earthquakes here. And so, again, one caution about application of codes, AASHTO code in particular, AASHTO guide spec. There's something called capacity protection that we do in bridge design that I don't know that it has a corollary in building design necessarily, which is to say there's certain elements, principally the foundation, that you don't want to go inelastic. So you design what's essentially a fuse in your structure so that you have all your inelastic behavior is outside the foundation zone. And you apply a factor to that, a strength increase factor for your material properties. So that's the basis for your foundation design, and the kind of the fundamental basis, universal basis in the AASHTO guide spec for seismic. The presumption is that lateral forces control your design, which, of course, on the West Coast, certainly in California, they do, but they don't everywhere. And it also assumes that this capacity protection is feasible. And if you look at the history for ductility-based design, the principle that is, I'm sure you're all aware of, is that your inelastic displacement demand is going to be about the same as your elastic displacement demand. So you can look at these elements and you factor your demands, if you want to, your displacement demand, and get refine your design on these fusel elements so that you have what you see as a safe design because your foundation is essentially elastic. The rub comes in when you have a big bridge like Port Mann or other big bridges where the basis of your design is controlled by wind. And so if your lateral forces are controlled by wind and yet you still have the same criteria, you have to apply your overstrength factor to a design. You obviously don't design for wind inelastically, you design pseudo-elastically. You have a factor applied to a design based on wind, and you can very easily require double the foundation design in the best of circumstances by having to apply this capacity protection to a design that's reinforced where the main reinforcement is sized for wind. So we try, and frankly, very few jobs, you start with this discussion at the beginning of the job, and very few of these big bridges have been subjected to this, but it is a challenge to convince agencies what you need for rational design. An example that carries this further is, again, this Port Mann Tower. Again, the principle of superposition for these big bridges, when things are nonlinear, which they're fundamentally nonlinear really when you look at the progression of liquefaction, you really can't analyze to get your moments and forces and apply a factor to it. It doesn't make any sense. The rational approach is to apply some multiplier, if you will, on the ground motions and see how the overall system behaves. So what we do actually routinely is run a nonlinear time-dependent analysis with moment curvature definitions and soil properties that reflect the progression from non-liquefied to liquefied conditions, and where we need to have look at a margin or safety, that we apply that margin to the ground motion. The other point to be made here, by the way, and you could tell by, I think, visually looking at this picture, again, the notion of thinking for yourself, if you're the designer or the owner of that bridge, there's no torsional stiffness in this deck. I would say that the last place you would like to see a plastic hinge is at the base of that column. Because unlike a conventional girder bridge where you have stability afforded by the balance of the bridge, here, if you have inelastic response to that column, you're basically going to blow the bridge up when you're done. You'll have a residual drift that'll be, hopefully the residual drift is not as tall as the tower, but you'll have a condition that you just can't recover from. So we advocate for designing these. We detail them for confinement, just as though it were a capacity protected design, but we look at the entire superstructure and substructure system as a unit. Lastly, I mentioned these layered systems, and this is something that This little quote at the top was something that Harvard Grant, back in the day, I'm old enough that we had computer rooms when I started engineering also at Harvard. And this was a sign that he had over the computers in the computer room. I think it's honestly as true today as it was then. What you have now, the general analysis routines are far better today than they ever were before. And so you have much more robust and extensive capabilities that you had at the time. But there are specialized analysis routines that are needed for some situations that the general purpose programs don't do a good job with. And I'm still cautious with cradle to grave design algorithms. As a matter of course, we never design using one set of software anyway. We use multiple software to check, to have checks and balances. But there are certain things in software that, until very recently, I know of that were quite incorrect, this being one of them. I mentioned this layered system, and I know you all, once you got through your first statics class, realized that you formulate a stiffness matrix by taking your element and applying your unit displacement and looking at the forces, and that's your stiffness matrix. Well, if you are using a general purpose program or even a special purpose program that had this link system on the right internal to the program that you might not know about, what you have is you have I1 plus I2, and that doesn't equal I gross. There was actually a bridge that we worked on many years ago where the designer used this rigid link system and the steel demand was off by 30%. And fortunately, in fact generally, for a steel composite, obviously the steel is over-designed and the concrete is under-designed. So the tension in the concrete for cracking was more than double what it had forecast, and the steel demands, tension and compression, mostly compression in the bottom flange, was 30% too high. On that particular bridge, we just changed all the grade 70 steel to grade 50 and said that was good enough. But we actually had to build the bridge low and take all the stay cables and pull it up to externally pre-stress the deck to make up for the fact that when it was designed, it was not designed properly. But this is the kind of thing that I say it's in the big general purpose programs today. I know of only one that's still out there that might entail this kind of problem, and the main international ones all have very good, robust algorithms. But this is the type of thing you have to read the technical manual that comes with software and understand what they're doing. And if you don't understand what they're doing or they don't tell you, you're probably better off buying a different program. So that's what I have, and I have little time for questions. Thank you for your attention.
Thank you very much. Oh, sure.
Question or mic for questions?
Good evening.
Hi.
Kwame Ajari. I'm a director at the American Society of Civil Engineers. You mentioned that codes are restrictive. Is that more of a commentary that the process to change the codes is very cumbersome and you can't get them to reflect what the practitioners see out there should be, what the code should be?
It's both. I mean, the process is, as it should be, is fairly extensive to get codes changed, because codes are mostly consensus bodies, and so you have dissent that can either derail or certainly delay modifying a code. But they also can be restrictive in that they're mostly, at least in the U.S., they're mostly prescriptive. They tell you how to affect your design, basically how to do your calculation for a specific mode of behavior. And that doesn't always lend to innovation and progressive design there. And they vary. Part of the issue in the U.S. is while there's an AASHTO code, there's also 50 states. And every state has their own implementation. And there's some significant disparities in terms of fundamental application from one state to the next that just get to be so prescriptive. And to give due to the agencies just don't want to have a problem. And so if they have an experience in their backlog that says, this type of design in a certain instance was a problem, I'm going to basically write it out in my prescriptive requirements. Yet that history may have no relevance to what you're trying to design at the time. So.
Thanks. Maybe I'll sneak in another quick question. What's your opinion on what's going on with the Millennial Tower in San Francisco?
Any other questions?
Yeah, I mean, the last I heard, they were going to put micropiles in. It's, I have nothing to do with the tower, and I don't really know the people or most of the people that were involved with it. But I expect that the decision to keep those tips up as high as they did was clearly an economic decision, but also one with which they had some degree of confidence at the time. And geotechnical engineering is there's still a lot of mystery in it, and being obviously hindsight's 20/20, it would have been far cheaper to go down than put in all these micropiles or whatever they're going to do. But I can understand. I don't know what the circumstances were and what the pressures were to save money, but I certainly can appreciate that you get into situations, you get an inordinate amount of pressure to cut price. I mean, if you look at the vintage example of this is the Tacoma Narrows, first Tacoma Narrows bridge that flew apart. That bridge, the history is not as well known as the video, but the history of that bridge is that it was originally designed, and there was an expert panel that put together the design, and that design was rejected because it was too expensive. And so they went back. They said, give me a more economical design, which when they ended up with the plate girder design that had been used in New York, but it was a much wider bridge in New York. And actually, when the bridge collapsed, they were in the process of making fairings for the bridge. But that was, pardon my disdain for the DOT at the time, but the DOT engineer who pressured that engineering group, Moisef and others, into modifying the design was, if you read the history, actually the contractor that I worked for down in Oregon, the predecessor of that firm was the firm that built the first Tacoma Narrows Bridge, and they had quite interesting documentation on it. That individual that applied that pressure didn't take much credit for that economical design that fell down. And he took a lot of credit for the stiffening truss that went back up. But that was a case where those engineers were pressured into doing something that they couldn't prove at the time was wrong. But it's not what they would have chosen to do if they would have been left to their own devices. And I can see something like that happen on the Millennial Tower. If you can't, there are times when you have to be just stubborn as a mule if you have this intuition, and I've faced these conditions myself when you get economic pressures and you can't prove that it's wrong. You can get compelled to do something that turns out to be not so smart, and you just have to be stubborn enough to just say no.
Hey, Piedmont Cars. It is known that bridges are serving as an example how we make progress and changes in approach through failure. The stories written, among others, by Professor Billington. What is right now on the drafting board that you think will serve as an example of failure that will lead to the next generation of bridges?
Remind me, who's the professor from Duke that's written about engineers human?
Petrosky, Henry Petrosky.
Yeah, I think Petrosky probably has this situation pegged, forecast a little bit better, is that what happens is when technologies are relatively new, they're limited in application by those who are well enough versed to be able to master them and understand their frailties and weaknesses and risks. And as they become more commonplace, there's a broader group of purveyors, of engineers who believe that if somebody else can do it, I can do it without knowing the details. And that's probably a bigger risk to me, I think, and historically has been a bigger risk. Tacoma Narrows perhaps accepted as an exception, but so there are bridge types, and the Cablestay Bridge, has been being pushed to pretty extreme limits of over 1,000 meters of span. There'll be a time when you get cables so long you can't get them to stop vibrating, and I think some of the avant-garde architecture is done with some peril in that, at least from a durability standpoint, I would say that that's certainly a reason for caution on some of the bridges that are built more for architectural flair than for utility. But it's what you're comfortable with, you're not worried about. It's the unknown that you worry about. So I don't worry about Cablestay bridges, but there are aspects of where I certainly do see applications which are, I think, less than prudent, that are out there. Again, cable vibration and anchorage design and things being among them. But then my competitor would say I'm just sour grapes, and that's my competitive position. So, which maybe it is, but.
Thank you.
So now we need one younger person to ask the question.
So one of the questions I have looking at some of the bridges is the bridge designer doesn't really look into maintenance and inspection processes because there's a lot of money into maintaining inspection after the bridge is being done. What's your comments on the designer actually look into the maintenance, inspection, operation process, or just make a bridge pretty? The delivery vehicle for a bridge design has an awful lot to do with that. The traditional way of delivering a bridge design is we do a design for the owner passes it out, puts it on the street for a bid, contractors bid it, and then they build it. And the engineer may or may not have a lot of interface with that construction side of things. But that filter goes through the owner and the owner's engineering organization in the case of an agency. And so they determine what your criteria is. And if they don't have maintenance criteria, then you don't have a focus on maintenance criteria. The other end of the spectrum is a P3, a concession job, where you have private money, generally toll financed, and I can assure you that you spend a lot of time on maintenance because all that concessionaire cares about is never having to tell a car that he can't pay $3 and go across that bridge. So we spend an awful lot of time on maintainability, on designing elements like either getting rid of joints or having joints that are in segments so you don't have to shut down traffic, of having access for inspection. So it really depends on the what the criteria is, what this project criteria is when you get going. So there are bridges where we do, an awful lot of the basic configuration is centered around maintenance and maintainability, and then there are those where it's given very little consideration.
One question from a young person.
ask questions this afternoon.
So you mentioned that a design should not cause emotional injury, and sometimes architects want to do stuff because it's poetic or because it looks good. So as an engineer, how much do you think, I mean, how important is that, and how much weightage would you give to that?
Okay, obviously, you know, I'm an engineer, not an architect. And we have had projects where we have 2 or 3 architects because of the different participants on the job, on the same job. And I don't recall that we ever had 2 architects agree on anything. So there is a perspective as to what is embellishment and what is, you know, the form of the bridge, the appropriate form of the bridge. And it's not, you know, it's a fairly general debate of you know, generally we, and again, Arvid's approach to it was if you are really efficient with your design, your aesthetics will follow the design and it'll take care of itself. But certainly shapes and shadows and things do make a difference, and they're very low cost overhead. But changing a structural form for architectural reasons is usually very costly and inefficient. And there are some people that advocate that, and it's certainly done. But I would say most engineers are not going to be of that frame of mind. The infusion of architects into our business is really something in the last 10 years, maybe a little bit longer than that. And even today, we have architects in our own firm, and the reason we like them in our own firm because I'm the boss and I get to tell them what to do rather than the other way around. So, you know, there are some beautiful designs, grandiose designs. I mean, Santiago Calatrava is world famous, and some of his bridges I admire greatly, and some of them not so much, in terms of their, you know, the expression of utility, if you will. I was in a conference in Paris where there was presentations on the bridges in France, one of them being the Pont d'Europe in Orléans. And I sat in the back of the room and watched a raging debate between the pro and anti, Santiago Calatrava wasn't there, the pro and anti-Calatrava people, and there were equal numbers on both sides of the aisle, had a very vigorous argument about what was appropriate and what was not. And I think that's, you know, that's unavoidable. People have different perspectives on things, and there are clients, more private clients, I think, than public ones, hopefully, that are willing to invest in a spectacular architecture, a marquee. Usually, my own view is that when you're doing public money, using public money, you have a responsibility to be reasonably prudent with that money. And I'm less inclined to put embellishment on a bridge.
I noticed it looks like we're just past 6, so maybe we'll wrap it up. I just wanted to thank David, to someone who comes out who, you know, designs with his team these incredible structures. And next time we're at Hoover Dam, think about that, or visiting some of these others. It's just a real treat. And thank everybody for kind of coming out and your attention this afternoon. So.